Tonight, we're going to follow a single spacecraft on the longest journey ever taken. A machine no bigger than a small car, launched in 1977, now racing through the absolute darkness between the stars. Voyager 1 is the most distant human-made object in existence, and it's never coming back. But here's what's going to blow your mind. Right now, after nearly half a century of travel, after crossing the boundary of our solar system, after becoming the first human object to enter interstellar space, Voyager 1 has barely started its journey. In 1 million years, this spacecraft will have traveled distances that make our solar system look like a grain of sand on an endless beach. And by the end of tonight, you're going to understand exactly where it's going, what it will encounter, and why this journey is one of the most profound things humanity has ever done. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. September 5th, 1977, Cape Canaveral, Florida. A Titan IIIe rocket sits on the launch pad, carrying a payload that weighs about 825 kilograms or 1,820 pounds. That payload is Voyager 1, though at this moment it's just a collection of cameras, instruments, computers, and a large antenna, all built around a framework of aluminum and titanium. But this is no ordinary machine. Every component was designed to survive decades in the harsh environment of space. The main antenna, 3.7 meters across, or about 12 feet, points back toward Earth, maintaining constant communication across billions of miles. Extending from the spacecraft on long booms are the magnetometer and the radioisotope thermoelectric generator, the RTG, Voyager's power source. The RTG contains plutonium-238 that generates heat as it decays, converted into about 470 watts of electricity at launch. That's barely enough to run 5 old light bulbs, but it powers all of Voyager's systems. The plutonium has a half-life of 87.7 years, so the power slowly decreases over time. Eventually, in the late 2030s or early 2040s, the power will drop too low to operate any instruments, and Voyager will go silent. The spacecraft carries cameras, spectrometers, and instruments to detect cosmic rays, plasma, and magnetic fields. The computer controlling everything has just 69 kilobytes of memory, millions of times less than a modern smartphone, but it has operated flawlessly for nearly 50 years. NASA expects the mission to last maybe 5 years. But nobody imagines this machine will still be functioning nearly half a century later, still sending data back from beyond the edge of the solar system. The rocket ignites. Flames pour from the engines. The ground shakes. And Voyager 1 begins its ascent, climbing slowly at first, then faster, punching through the atmosphere, shedding its rocket stages one by one, until finally it's free, released into space on a trajectory that will take it toward Jupiter. The spacecraft isn't particularly fast at this point. It's traveling at roughly 25,000 miles per hour, or about 40,000 kilometers per hour, relative to Earth. That sounds fast, but space is vast beyond comprehension, and at this speed, reaching even the nearest star would take tens of thousands of years. Fortunately, Voyager 1 has a trick up its sleeve, a technique called a gravity assist, or gravitational slingshot. The basic idea is brilliant. When a spacecraft passes close to a planet, the planet's gravity pulls on it, changing its trajectory and speed. If you approach the planet from behind, relative to the planet's orbital motion, and swing past it in just the right way, you can steal a tiny bit of the planet's orbital momentum. The planet slows down by an imperceptibly small amount, and the spacecraft speeds up significantly. It's like grabbing onto a fast-moving merry-go-round as you run past it. Jupiter is orbiting the Sun at about 8 miles per second, or about 13 kilometers per second. The spacecraft swings around Jupiter in a curved path, and when it leaves, it's not just moving at its original speed, but at that speed in a reference frame that's itself moving at about 8 miles per second, or about 13 kilometers per second. For Voyager 1's encounter with Jupiter, the gravity assist added about 9 miles per second, or about 15 kilometers per second, to its velocity. That boost makes all the difference. This technique was first demonstrated with the Mariner 10 mission in the mid-1970s. But Voyager's Grand Tour was designed to use multiple gravity assists to visit several planets in sequence. The outer planets aligned favorably only once every 176 years, and NASA seized the opportunity. March 5, 1979. Voyager 1 reaches Jupiter after traveling for roughly a year and a half, covering about 400 million miles, or about 650 million kilometers. Jupiter is enormous, about 318 times more massive than Earth, with a gravitational field strong enough to hold dozens of moons in orbit. As Voyager approaches, its cameras begin returning images that stun scientists back on Earth. The Great Red Spot, a storm larger than Earth itself, swirls in Jupiter's southern hemisphere. This storm has been observed for at least 300 years, rotating counterclockwise, with winds at hundreds of miles per hour, or hundreds of kilometers per hour. The cloud bands show intricate details never seen before, with alternating light zones where gas rises and dark belts where it descends, all driven by powerful jet streams. Lightning flashes in the atmosphere, detected as radio bursts millions of times stronger than terrestrial lightning. The magnetic field is intense, about 20,000 times stronger than Earth's, creating radiation belts so severe they threaten the spacecraft's electronics. And the moons are revealed as worlds in their own right. Io, the innermost large moon, is covered in active volcanoes, the first time volcanism has been observed anywhere other than Earth. Navigation engineer Linda Morabito discovered the volcanism when she noticed a volcanic plume erupting 186 miles above Io's surface. The volcanism is driven by tidal heating as Jupiter and the other moons constantly flex Io's interior, making it the most volcanically active body in the solar system. Europa shows a smooth, icy surface crisscrossed with cracks, suggesting a liquid ocean beneath the ice, making it one of the most promising places to search for life beyond Earth. Ganymede and Callisto display ancient, cratered landscapes, showing billions of years of impacts. By the time Voyager leaves Jupiter, it has transformed our understanding of the Jovian system. But Voyager 1 isn't here just to sightsee. It's here to use Jupiter's gravity to accelerate towards Saturn. The spacecraft swings past Jupiter on a carefully calculated trajectory, passing within about 173,000 miles, or about 278,000 kilometers, of the planet's cloud tops. Jupiter's immense gravity pulls on Voyager, bending its path and flinging it outward towards Saturn at a much higher speed. By the time Voyager 1 leaves Jupiter's sphere of influence, it's traveling at about 34,000 miles per hour, or about 55,000 kilometers per hour, relative to the Sun, gaining about 9,000 miles per hour, or about 15,000 kilometers per hour, from the gravity assist. That boost is what allows Voyager to reach Saturn and eventually leave the solar system entirely. November 12, 1980. Voyager 1 arrives at Saturn, the ringed giant of the outer solar system. The journey from Jupiter to Saturn took about 1 year and 8 months, covering another 930 million miles, or about 1.5 billion kilometers. Saturn is the second largest planet in the solar system, about 95 times more massive than Earth. Its density is so low that if you could find an ocean large enough, Saturn would float in it. The approach images are spectacular. Saturn's rings, seen in unprecedented detail, reveal thousands of individual ringlets, gaps, and structures created by gravitational interactions with Saturn's many moons. From Earth, the rings appear as a smooth structure divided into a few broad bands, including the Cassini division between the A and B rings, discovered in 1675. But Voyager reveals far more complexity. The rings are composed of countless individual particles, ranging from tiny grains to house-sized chunks, each one essentially a tiny moon orbiting Saturn independently. The particles are mostly water ice, with traces of rocky material. The rings extend about 41,000 miles radially, but are only about 33 feet thick. If you scaled them down to the size of a football field, they'd be thinner than a sheet of paper. Voyager's images show structure that can only be explained by gravitational interactions. Shepherd moons orbit just inside or outside narrow rings, keeping particles confined. Density waves and bending waves are created by resonances with more distant moons propagating through the rings in elegant patterns. The spacecraft passes within about 77,000 miles, or about 124,000 kilometers, of Saturn's cloud tops, close enough to get detailed images, but far enough to avoid the intense radiation near the planet. Saturn's magnetic field is weaker than Jupiter's, but still substantial, about 578 times stronger than Earth's magnetic field. Like Jupiter, Saturn has radiation belts, though less intense. The rings themselves absorb some of the charged particles, creating gaps in the radiation belts where the rings orbit. One of the primary targets is Titan, Saturn's largest moon and the only moon in the solar system with a thick atmosphere. Titan is enormous, larger than Mercury, with a diameter of about 3,200 miles, or about 5,150 kilometers. The thick atmosphere, rich in nitrogen and hydrocarbons, completely obscures the surface. Voyager 1 passes just 4,000 miles, or about 6,500 kilometers, above Titan's surface. The data reveals an atmosphere composed mostly of nitrogen, about 98%, with methane and other organic compounds. The surface temperature is about 94 Kelvin, or about -290 Fahrenheit, or about -179 Celsius. At this temperature, methane can exist as gas, liquid, or solid, raising the possibility of a methane cycle like Earth's water cycle. The atmosphere is eerily similar to Earth's early atmosphere before life filled it with oxygen, making Titan a natural laboratory for studying prebiotic chemistry. After the Titan flyby, Saturn's gravity gives Voyager one another boost, but this time the trajectory is different. Instead of being flung to another planet, Voyager is sent upward relative to the plane of the solar system, on a path that will take it out of the planetary realm entirely. The close approach to Titan dictated this trajectory. To pass close enough to Titan to gather useful data, Voyager had to approach Saturn at a particular angle. That angle meant that after the encounter, Voyager would be heading north relative to the ecliptic, the plane in which the planets orbit. This trajectory precluded any chance of continuing on to Uranus and Neptune. Those planets lie in the ecliptic plane, and reaching them would require a southward trajectory from Saturn. Voyager 2, which visited Saturn a few months after Voyager 1, took a different trajectory that allowed it to continue to Uranus in 1986 and Neptune in 1989. After the Saturn encounter, Voyager 1 is moving at about 10.5 miles per second, or about 17 kilometers per second, relative to the Sun. That's faster than any other human-made object has ever traveled. It's fast enough that Voyager will cross the heliopause, the boundary of the solar system's magnetic influence, in about 3 decades. The primary mission is complete. Voyager 1 has visited Jupiter and Saturn, returned thousands of images, discovered new moons, and fundamentally changed our understanding of the outer solar system. But the spacecraft is still functioning perfectly. Its nuclear power source still has decades of power left, and Voyager is heading somewhere no human-made object has ever gone before. Out beyond the planets, into the vast space between the Sun and the stars. The Voyager Interstellar mission begins. To understand where Voyager 1 is going, you need to understand what interstellar space actually means. Most people think the solar system ends at Neptune, but the true boundary is much farther out. The Sun constantly emits a stream of charged particles, electrons and protons, flowing outward at hundreds of miles per second or hundreds of kilometers per second. This is the solar wind, and it creates a bubble around the Sun called the heliosphere. The solar wind originates in the Sun's corona, where temperatures reach millions of degrees. At these extreme temperatures, atoms are stripped of electrons, creating plasma that streams outward, carrying the Sun's magnetic field with it. Near Earth, the solar wind flows at about 250 miles per second, or about 400 kilometers per second. As it expands outward, it gets less dense, but it still dominates the environment throughout the inner solar system. Inside the heliosphere, the magnetic field is the Sun's field, twisted by the solar wind's flow. Outside, the solar wind gives way to the interstellar medium, the incredibly diffuse gas and dust filling space between stars. The interstellar medium contains about 1 atom per cubic centimeter, on average, mostly hydrogen, with cosmic rays accelerated by supernova explosions, traveling at significant fractions of light speed. The boundary between these regions is the heliopause, where the pressure from the solar wind equals the pressure from the interstellar medium. The heliopause isn't a sharp wall, but a transition region, possibly hundreds or thousands of miles thick. For decades, nobody knew exactly where it was. Estimates placed it somewhere between 80 and 100 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, about 93 million miles, or about 150 million kilometers. So the heliopause was expected roughly 3 times farther than Neptune's orbit. Voyager 1 would find out exactly where. August 25th, 2012. Voyager 1 is about 11 billion miles, or about 18 billion kilometers, from the Sun, roughly 121 astronomical units. After nearly 35 years of travel, the spacecraft's instruments detect a sudden change. The intensity of galactic cosmic rays increases sharply by about 5%, then another 5%. Cosmic rays are mostly blocked by the solar wind inside the heliosphere, so increasing intensity suggests Voyager is approaching or crossing the heliopause. At the same time, the intensity of lower energy particles from the Sun drops dramatically. The plasma detector shows the solar wind has decreased. This is exactly what you'd expect at the heliopause. But there's a problem. The magnetic field direction, which should change at the heliopause, remains pointing the same direction. Inside the heliosphere, the field is the Sun's field twisted into a spiral. Outside, it should be the interstellar magnetic field with a different orientation. The field should change abruptly, but it doesn't. Scientists are puzzled. Has Voyager crossed the boundary or not? For months, they debate the data. Some think Voyager entered a boundary layer between the heliosphere and interstellar space. Others think it's approaching the edge, but hasn't crossed yet. The debate continues through late 2012 into 2013. Radio signals now take 17 hours to travel from Voyager to Earth, making communication painfully slow. September 12, 2013. Scientists announced that Voyager 1 crossed the heliopause on August 25, 2012. Careful analysis shows Voyager did cross into interstellar space. The spacecraft is now outside the bubble of the Sun's influence, the first human-made object to reach interstellar space. But here's the thing that most people don't understand. Interstellar space doesn't mean Voyager has left the solar system. Not even close. The Sun's gravitational influence extends much, much farther than the heliopause. Far beyond the planets, beyond the Kuiper belt where Pluto orbits, beyond even the heliopause, there's a vast region of icy bodies orbiting the Sun in a spherical cloud. This is the Oort cloud, named after the Dutch astronomer Jan Oort, who first theorized its existence in 1950. The Oort cloud contains billions of icy objects, remnants from the formation of the solar system, orbiting at distances from about 2,000 to 100,000 astronomical units. That's roughly 2 light-years away. A light-year is the distance light travels in 1 year, almost 6 trillion miles, or about 9.5 trillion kilometers. Voyager 1 is currently only about 160 astronomical units from the Sun. It has traveled only 0.008% of the distance to the outer edge of the Oort cloud. At its current speed, it will take Voyager roughly 300 years just to enter the inner edge of the Oort cloud, and another 30,000 years to pass through it completely. 30,000 years from now, human civilization as we know it may not exist, and Voyager 1 will still be out there, drifting silently through the darkness. Now let's jump forward. Way forward. 1 million years into the future. What will the universe look like? Where will Voyager 1 be? First, let's establish some context for how far Voyager will have traveled. At about 10.5 miles per second, or 17 kilometers per second, over the course of 1 million years, Voyager 1 will travel approximately 333 trillion miles, or about 536 trillion kilometers. To put this in perspective, that's roughly 56,000 light-years. Remember, our entire solar system, including the Oort cloud, extends only about 2 light-years from the Sun. In 1 million years, Voyager 1 will have traveled 28,000 times farther than the outer edge of the solar system. The Milky Way galaxy, our home galaxy, is about 100,000 light-years across. So Voyager will have traveled more than halfway across the galaxy. Except, of course, it's not actually going to make it halfway across, because Voyager is traveling through space, not through a galaxy. It's moving through the local interstellar medium, the incredibly diffuse gas and dust that fills the space between stars. And it's doing so at a relatively modest speed by cosmic standards. Stars in our region of the galaxy are typically moving at speeds of a few hundred miles per second or a few hundred kilometers per second relative to the galactic center. Voyager, at about 10.5 miles per second, or about 17 kilometers per second, is actually moving slower than most stars. What this means is that over the course of 1 million years, Voyager won't just be moving farther away from the Sun. It will also be passed by countless stars, some of which might come relatively close. How close? Let's look at some specific predictions. The stars in our region of the galaxy are not stationary. They're all orbiting the galactic center, taking about 225 million years to complete one orbit. But they're not all moving at exactly the same speed or in exactly the same direction. There's a random component to their motion, like cars on a highway, all going roughly the same direction, but at slightly different speeds and in different lanes. This means that over long periods of time, stars can pass relatively close to each other. In fact, every few million years or so, a star passes within about 1 light year of our Sun. And every few tens of millions of years, a star might pass within about half a light year, close enough to potentially disturb the Oort cloud and send comets falling toward the inner solar system. Voyager 1, traveling through this same region of space, will occasionally pass near other stars as well. Astronomers have calculated the trajectories of nearby stars and Voyager's path to predict which stars Voyager might pass close to over the next few million years. The results are fascinating. The closest approach Voyager 1 will make to another star in the next million years will happen in about 40,000 years. The star is Gliese 445, also known as A's, plus 79 degrees, 3,888. It's a small red dwarf star, much smaller and dimmer than our Sun, located about 17.5 light-years from us right now. But Gliese 445 is moving toward our solar system. In about 40,000 years, it will pass within about 3.5 light-years of the Sun. At that time, Voyager 1 will be in roughly the same region of space, and calculations suggest it will pass within about 1.5 light-years of Gliese 445. 1.5 light-years is still an enormous distance. That's about 90,000 astronomical units, or roughly 9 trillion miles. At that distance, Gliese 445 will be nothing more than a faint point of light to Voyager's cameras, if they were still functioning, which they almost certainly won't be. But it's still the closest Voyager will get to another star for a very long time. After that, Voyager will continue on its journey, passing through the vast empty spaces between stars. Over the next few 100,000 years, it won't come particularly close to any other stars. It will just keep drifting, moving at a constant speed, following the trajectory set by its final gravitational encounter with Saturn over 1 million years ago in the late 20th century. Let's jump ahead to 100,000 years from now. Voyager 1 has traveled about 5.5 light-years from the Sun. That's farther than the distance to the nearest stars, Alpha Centauri and Proxima Centauri, though Voyager isn't heading toward them. At this point, the Sun would be just another star in Voyager's sky, if anyone were looking. Not the brightest star, not particularly special, just one star among hundreds of billions. Earth, of course, would be completely invisible, lost in the glare of the Sun at this distance. the spacecraft itself, assuming it hasn't been destroyed by a collision with an interstellar dust, grain, or larger object, would be cold and dead. The radioisotope thermoelectric generator that powers Voyager will have run out of usable fuel within a few decades of 2026. Already, NASA has been shutting down instruments one by one to conserve power. By the late 2030s or early 2040s, Voyager will go silent, no longer able to transmit data back to Earth. At that point, it becomes a derelict, a piece of metal and plastic and circuitry drifting through the void. But it doesn't disappear. It doesn't decay, at least not in any meaningful way. In the near vacuum of interstellar space, there's no oxygen to cause rust, no water to cause corrosion, no bacteria or weather to break down materials. Voyager will remain essentially unchanged for millions, possibly billions of years. The gold-plated copper records attached to the spacecraft, carrying sounds and images from Earth, will remain intact, their information preserved in the grooves of the disk. If an alien civilization were to somehow find Voyager, even millions of years from now, they could potentially extract that information and learn about humanity. Of course, the chances of that happening are vanishingly small. Space is so incomprehensibly vast that the probability of Voyager ever encountering another civilization, or even another star system with planets, is effectively zero. But the possibility exists, and that's part of what makes Voyager's journey so poignant. It's a message in a bottle, thrown into an ocean so vast that it will almost certainly never be found. But almost certainly is not the same as certainly. 200,000 years from now. Voyager 1 has traveled about 11 light-years. It's now in a region of space populated by a different set of nearby stars than the ones we see in our night sky today. The constellations, those familiar patterns of stars that have guided human navigation and mythology for thousands of years, would be unrecognizable to anyone from Earth looking at the sky from Voyager's position. Orion, the Big Dipper, Cassiopeia, all the familiar patterns are gone, replaced by new arrangements that would mean nothing to us. This is because the stars are all moving relative to each other. Over thousands and tens of thousands of years, their positions shift enough that the constellation patterns change. Over hundreds of thousands of years, the changes become dramatic. The night sky of Earth, 200,000 years from now, assuming Earth still exists and still has observers, would look significantly different from the night sky today. Stars that are bright and prominent now will have moved or dimmed or even exploded. New stars will have appeared in positions that are currently empty. And the overall pattern, the fabric of the night sky, will have been rewoven into something new. Voyager, meanwhile, continues its journey, unaware and uncaring of these changes. It's traveling in a straight line, or as close to a straight line as possible, given the tiny gravitational tugs from distant stars and the overall galactic gravitational field. Its velocity relative to the Sun has barely changed. There's nothing in interstellar space to slow it down. No air resistance, no friction, no drag of any kind. Newton's first law states that an object in motion stays in motion unless acted upon by an external force. In the near-perfect vacuum of space, there are essentially no forces acting on Voyager. So, it continues moving at the same 10.5 miles per second, or about 17 kilometers per second, it had when it left the solar system's influence, minus tiny, almost negligible amounts lost to interactions with the sparse interstellar medium. 500,000 years from now, Voyager has traveled about 28 light-years. At this point, it has definitively left the Sun's neighborhood. The stars that were our Sun's closest neighbors when Voyager launched, stars like Alpha Centauri and Barnard's star and Sirius, are now far behind. Voyager is in a different part of the local stellar neighborhood, surrounded by stars that would have been distant and faint from Earth's perspective in the 20th century. If intelligent life exists in this region, and if they have the technology to detect small, cold objects drifting through space, they might notice Voyager. They might see it as an anomaly, a piece of metal and plastic moving through the void, clearly artificial, clearly not a natural object. They might investigate. They might decode the golden record. They might learn about a species that lived on a small planet orbiting a yellow star many light years away, a species that built this machine and sent it out into the universe as an ambassador of sorts. Or they might not. They might miss it entirely, or notice it and dismiss it as debris, or notice it and study it, but fail to understand its significance. Or, most likely, there is no intelligent life in this region to notice Voyager at all. The galaxy is vast, and intelligent technological civilizations capable of building spacecraft and detecting objects in interstellar space might be incredibly rare. We simply don't know. Humanity has been searching for signs of extraterrestrial intelligence for decades, using radio telescopes to listen for signals from other civilizations. So far, we've heard nothing but silence. That could mean we're alone, or it could mean civilizations are too far apart in space or time to ever communicate. Or it could mean they exist, but don't broadcast signals we can detect. We don't have enough data to know. 750,000 years from now, Voyager has traveled about 42 light-years. It's now deep in the Orion arm of the Milky Way, the spiral arm where our solar system resides. The galaxy is structured like a spiral, with arms of denser star concentrations radiating out from the central bulge. Our Sun is located in a minor arm called the Orion arm, or Orion's spur, positioned between two major arms, the Perseus arm and the Sagittarius arm. Voyager, having traveled 42 light-years, is still within this same general region. It hasn't crossed into a different spiral arm. That would require traveling hundreds or thousands of light-years, far beyond what Voyager will accomplish in 1 million years. But even within the Orion arm, the stellar density varies. Some regions have more stars clustered closer together, while other regions are more sparse. Voyager is passing through these varying densities, sometimes traveling through regions where stars are relatively numerous, other times through regions where the nearest star is many light-years away. In the dense regions, there's a slightly higher chance of passing close to a star, though still an incredibly tiny chance. In the sparse regions, Voyager could go tens of thousands of years without coming within 10 light-years of any star. 1 million years from now. Voyager 1 has traveled approximately 56,000 light-years. But here's where we need to stop and address something important. That 56,000 light-year figure is a straight-line calculation based on Voyager's current velocity relative to the Sun. It assumes Voyager continues moving in a straight line at a constant speed for the entire million years. In reality, things are more complicated. The galaxy is not a static environment. It's rotating, and everything in it, including the Sun and Voyager and all the stars around them, is orbiting the galactic center. The Sun takes about 225 million years to complete one orbit around the galaxy. Voyager, having been flung out of the solar system at a particular velocity relative to the Sun, has its own trajectory through the galaxy that doesn't exactly match the Sun's orbit. Over 1 million years, which is less than 1% of a full galactic orbit, the differences in their paths become noticeable. Calculating Voyager's exact position relative to the galactic center after 1 million years requires detailed simulations that account for the gravitational influence of the galaxy's mass, distribution, the motions of nearby stars, and the overall rotation of the galactic disk. These simulations have been done by astronomers, and they show that Voyager's path curves slightly due to the galaxy's gravity. It's not traveling in a perfectly straight line. The galactic gravitational field, primarily from the dark matter halo that surrounds the visible galaxy, exerts a gentle pull that gradually bends Voyager's trajectory. After 1 million years, Voyager will have been pulled slightly toward the galactic plane and slightly in the direction of the galaxy's rotation. The exact position is hard to pin down precisely without running the full simulations, but we can make some reasonable estimates. Voyager will likely be somewhere between 50 and 60 light-years from where the Sun will be at that time. Note that this is the distance from the Sun's future position, not its current position. The Sun itself will have moved significantly over 1 million years, traveling about 1,000 light-years along its orbit around the galaxy. So if you're trying to visualize where Voyager will be in 1 million years, you need to think about where both Voyager and the Sun will be at that time, not where they are now. Both will have moved, and the distance between them will have grown to about 50 to 60 light-years, plus the additional distance from the Sun's own orbital motion. What will the universe look like 1 million years from now? From Voyager's perspective, not much will have changed on the largest scales. The galaxy will still be the same basic shape, a barred spiral with arms wrapping around a central bulge. The supermassive black hole at the center, Sagittarius A, will still be there, about 4 million times the mass of the Sun, quietly accreting matter and occasionally flaring when it swallows gas or a stray star. The Andromeda Galaxy, our nearest large galactic neighbor, will be slightly closer than it is today. Andromeda is currently about 2.5 million light-years away and approaching us at about 68 miles per second, or about 110 kilometers per second. In 1 million years, it will have closed the distance by about 110,000 light-years. That's still far enough away that the two galaxies haven't started to interact significantly, but the approach is ongoing. In about 4 billion years, give or take, Andromeda and the Milky Way will collide and merge, creating a new, larger elliptical galaxy. But that's far in the future, long after Voyager's journey has become just one tiny event among countless others. The stars in Voyager's region of space will have changed. Some stars that exist today will have exploded as supernovae. Massive stars have lifetimes of only a few million to a few tens of millions of years. So, any really massive stars in Voyager's path will have already lived and died by 1 million years from now. Their explosions will have scattered heavy elements into the interstellar medium, enriching the gas that will eventually form new stars and planets. Other stars, smaller and longer-lived, will still be around, continuing their slow burn through hydrogen fusion. Red dwarf stars, the smallest and most common type of star, can live for hundreds of billions or even trillions of years. The red dwarfs that exist today will still be shining 1 million years from now, virtually unchanged. New stars will have formed from collapsing gas clouds. Star formation is an ongoing process in the galaxy, with new stars being born all the time in regions where gas clouds collapse under their own gravity. Some of these new stars will be in the region where Voyager is traveling, adding to the local stellar population. From Earth's perspective, assuming Earth still exists and has intelligent observers, Voyager 1 will have been forgotten for hundreds of thousands of years. The spacecraft went silent sometime in the late 2030s or early 2040s, once its power source ran out. After that, it became impossible to track. We know its trajectory based on the last signals we received, but without active tracking, without signals bouncing back, telling us its exact position, uncertainty grows. Over decades, we can still estimate its position fairly accurately. Over centuries, the uncertainty grows larger. Over thousands of years, we lose track of it entirely. By 1 million years from now, humanity, if it still exists in any form we would recognize, will have no idea where Voyager 1 is. The spacecraft will be a historical footnote, a relic from an ancient era when humans first began exploring space. Its exact fate, whether it's still intact, whether it passed close to any stars, whether it encountered anything unusual, all of that will be unknown. Unless, of course, some incredibly advanced future civilization develops technology to search for and locate ancient spacecraft drifting through the galaxy. But even that seems unlikely. Why would anyone go to the trouble of finding a tiny, silent, defunct probe when there are billions of other objects and phenomena to study? Voyager's journey will be lonely and anonymous. A quiet drift through the darkness, with no one watching and no one knowing. Let's think about what might happen to Voyager over this immense timescale. The spacecraft is traveling through what we call the local interstellar medium. This is the gas and dust that fills the space between stars in our region of the galaxy. It's not uniform. Some regions are denser, some are more sparse. Some regions contain mostly neutral hydrogen atoms, others contain ionized plasma. Some regions have stronger magnetic fields, others weaker. Voyager will pass through all these different environments over the course of 1 million years. Could it collide with something? In the densest regions of the interstellar medium, there's about 1 atom per cubic centimeter. That's 1 atom in a space about the size of a sugar cube. It's an almost perfect vacuum by any terrestrial standard. For comparison, Earth's atmosphere at sea level contains about 2.5 times 10 to the 19th power atoms per cubic centimeter. That's 25 billion atoms in the same sugar cube volume. The air you're breathing right now is incomprehensibly denser than the interstellar medium. So the interstellar medium is roughly 10 to the 19th power times less dense than Earth's atmosphere. To put this another way, if you took all the atoms in Earth's atmosphere and spread them evenly throughout a sphere with a radius equal to the Earth-Sun distance, 1 astronomical unit, you'd get a density similar to the interstellar medium. In such an environment, collisions with individual atoms are rare and have negligible effect. Voyager is moving at about 10.5 miles per second, or 17 kilometers per second, and when it hits an individual hydrogen or helium atom, the atom bounces off or gets swept aside, transferring an infinitesimally small amount of momentum. The energy of the collision is tiny. A hydrogen atom moving at about 10.5 miles per second, or 17 kilometers per second, has a kinetic energy of about 2.4 times 10 to the minus 19 power joules. That's far less than the energy of a single visible photon. Billions upon billions of these collisions would be needed to produce any measurable effect on Voyager's trajectory or speed. Over millions of years, These impacts might erode the spacecraft's surface very slightly, perhaps wearing away a few nanometers of material from the surfaces that face forward in Voyager's direction of travel. But it's not a significant effect. The spacecraft structure will remain essentially intact. The much bigger risk is hitting something larger. A dust grain, for example, or a small pebble-sized object. These are extremely rare in interstellar space, but they do exist. Grains of dust, typically a few micrometers to a few hundred micrometers across, are scattered throughout the galaxy. They're the remnants of dying stars, blown off in stellar winds or ejected in supernova explosions. Over billions of years, these grains accumulate, filling the space between stars with a very sparse haze. The dust grains are composed of various materials. Some are silicates, rocky minerals similar to sand. Some are carbonaceous, containing carbon compounds. Some are icy, coated with water ice or other frozen volatiles. Many are covered with complex organic molecules, created by chemical reactions driven by starlight and cosmic rays. If Voyager were to hit a dust grain at about 10.5 miles per second or 17 kilometers per second, the impact would be catastrophic for that part of the spacecraft. At those speeds, even a tiny grain carries enormous kinetic energy. A dust grain, with a mass of 1 microgram, about the mass of a grain of fine sand, traveling at about 10.5 miles per second, or 17 kilometers per second, has a kinetic energy of about 145 joules. That's roughly the energy of a 1 kilogram mass dropped from 15 meters, or about 50 feet. Concentrated into the tiny impact area of the dust grain, this energy is enough to vaporize the grain and punch a small crater in whatever part of Voyager it hit. The impact would create a tiny explosion, with the dust grain and some material from Voyager's surface both vaporizing from the heat generated by the collision. The crater would be small, perhaps a few millimeters across, but it would be permanent damage. If the grain hit a critical component, like the communications dish or one of the instruments, it could cause significant damage. A crater in the dish might affect its ability to focus radio waves. A hit on an instrument might destroy it entirely, though of course by the time Voyager is hit by such a grain, the instruments will have been dead for millions of years anyway. But the probability of such an impact is very low. The density of dust grains is so sparse that Voyager could travel for millions of years without hitting anything larger than an atom. Estimates vary, depending on assumptions about the dust density, but most models suggest that a spacecraft traveling through interstellar space might encounter a damaging impact once every few million to tens of millions of years. Over the course of 1 million years, there's perhaps a 10 to 20% chance that Voyager will be hit by something large enough to cause visible damage. That means there's an 80 to 90% chance it will remain essentially intact, its structure unchanged, except for minor erosion from atomic impacts. But there's also a small but real possibility it will be hit and damaged, or even destroyed, if it hits something large enough. The largest objects in interstellar space, aside from stars and planets, are rogue planets and asteroids that have been ejected from their parent solar systems. These are incredibly rare. Current estimates suggest there might be 1 or 2 rogue planets for every star in the galaxy. But they're spread across the vast volume of space, so the chance of Voyager hitting one is vanishingly small. Essentially, 0 over the course of 1 million years. More likely than hitting a rogue planet is passing through a dense molecular cloud. These are regions where the interstellar gas is much denser than average, perhaps hundreds or thousands of atoms per cubic centimeter instead of just one. Molecular clouds are where new stars form, and they can be enormous, spanning tens or hundreds of light years. If Voyager passes through a molecular cloud, it will experience higher erosion rates from the increased particle collisions. But even in a molecular cloud, the density is still far less than anything we'd consider a vacuum on Earth, so the effect will be minor. The spacecraft might lose a few more nanometers of surface material, but nothing that would threaten its structural integrity. Another question worth asking is whether Voyager could ever be perturbed onto a new trajectory by a close encounter with a star. We talked earlier about Gliese 445, the closest approach Voyager will make to another star in the near future, passing within about 1.5 light-years in about 40,000 years. At a distance of about 1.5 light-years, Gliese 445's gravity will have essentially no effect on Voyager's trajectory. Let's do the math to see why. The gravitational force between two objects is given by Newton's law of universal gravitation. The force equals the gravitational constant times the product of the two masses divided by the square of the distance between them. Gliese 445 is a red dwarf star with a mass about 12% of the Sun's mass. The Sun's mass is about 2 times 10 to the 30th power kilograms, so Gliese 445 has a mass of about 2.4 times 10 to the 29 power kilograms. Voyager's mass is about 825 kilograms. The distance at closest approach will be about 1.5 light-years, which is about 9 trillion miles, or about 14 trillion kilometers. Plugging these numbers into Newton's equation, the gravitational force is about 6 times 10 to the minus 14 power newtons. That's an incredibly tiny force. For comparison, the weight of a single human cell on Earth is about 1,000 times larger. This force will act on Voyager for the brief period when it's near Gliese 445, perhaps a few thousand years. The total change in Voyager's velocity will be immeasurably small, less than a millimeter per second. The gravitational force at that distance is far too weak to significantly alter Voyager's path. For a star to meaningfully change Voyager's trajectory, Voyager would need to pass within a few hundred astronomical units of the star, close enough that the star's gravity becomes significant compared to the general galactic gravitational field. At a distance of, say, 100 astronomical units, roughly the distance to the heliopause, a star like the Sun would exert a much stronger gravitational pull on Voyager. The force would be millions of times stronger than at 1.5 light-years. Such a close encounter could change Voyager's velocity by a few miles per second or a few kilometers per second, significantly altering its trajectory. But the probability of that happening is extremely low. Stars are very far apart compared to their sizes. The average distance between stars in our region of the galaxy is about 5 light-years. That's roughly 320,000 astronomical units. For Voyager to pass within a few hundred astronomical units of a star, it would have to get incredibly lucky, or unlucky depending on your perspective, threading the needle through a region of space where stars are rare and far between. The volume of space within a few hundred astronomical units of a star is tiny compared to the total volume of interstellar space. If we imagine a sphere with a radius of 100 astronomical units around a star, the volume is about 4 million cubic astronomical units. The volume of space within 5 light-years, the typical distance to the nearest star, is about 35 trillion cubic astronomical units. So the probability of passing within 100 astronomical units of a star, purely by random chance, is about 1 in 9 million. Over 1 million years, Voyager will pass through a region containing perhaps a few dozen stars. The probability that it will pass within 100 astronomical units of any of them is very small, though not zero. Most likely, all of Voyager's stellar encounters will be distant, at distances measured in light years rather than astronomical units. At those distances, the gravitational influence is negligible. Voyager will continue on its current trajectory, with only minor perturbations from distant gravitational influences. However, there is one force that will gradually change Voyager's trajectory over millions of years: the gravitational pull of the galaxy itself. The Milky Way is not just a collection of stars. It's a massive gravitational structure with a total mass of about 1 trillion times the mass of the Sun. Most of this mass is in the form of dark matter, invisible matter that doesn't emit or absorb light, but exerts gravitational force. The dark matter forms a halo around the galaxy, extending far beyond the visible disk of stars. This dark matter halo dominates the gravitational field in the outer regions of the galaxy, including where Voyager is traveling. The gravitational pull from the galaxy acts on everything in it, including Voyager. This pull is directed toward the galactic center and toward the galactic plane. If you're above the galactic plane, the gravity pulls you downward. If you're below it, the gravity pulls you upward. If you're moving away from the galactic center, the gravity pulls you back. For stars, this gravity is balanced by their orbital motion. Stars orbit the galactic center at speeds that exactly balance the gravitational pull, creating stable orbits that can last for billions of years. But Voyager is not in a stable orbit. It's moving at about 10.5 miles per second, or 17 kilometers per second, relative to the Sun, which is itself moving at about 137 miles per second, or about 220 kilometers per second, around the galactic center. Depending on Voyager's exact trajectory, it might be moving slightly faster or slightly slower than the circular velocity needed for a stable orbit at its distance from the galactic center. If it's moving slower, the galactic gravity will gradually pull it inward and downward toward the galactic plane. If it's moving faster, it will drift outward and continue away from the galactic plane. These changes happen very slowly. The galactic gravitational field is weak compared to the gravitational field near a star or planet. It takes millions of years for the galactic gravity to produce noticeable changes in Voyager's trajectory. Over 1 million years, Voyager's path will curve slightly. It won't be traveling in a straight line anymore. The trajectory will have bent by a small amount, perhaps a few degrees, due to the cumulative effect of the galactic gravitational field. This bending is small, but it's real. And it means that predicting Voyager's exact position after 1 million years requires taking into account the galaxy's gravitational influence. Simple calculations that assume Voyager travels in a straight line will be off by a noticeable amount. Now, let's talk about the golden record. Attached to the side of Voyager, one is a 12-inch gold-plated copper disc enclosed in an aluminum case. This is the Voyager Golden Record, a time capsule intended to communicate the story of Earth and humanity to any extraterrestrial intelligence that might find the spacecraft. The idea for the record came from Carl Sagan, the astronomer and science communicator who was a member of the Voyager imaging team. Sagan had previously worked on the Pioneer plaques, small metal plates attached to the Pioneer 10 and Pioneer 11 spacecraft that contained symbolic messages for any alien civilization that might find them. The plaques showed the figures of a man and woman, a diagram of the solar system showing Earth's location, and some basic information about hydrogen, the most common element in the universe. For Voyager, Sagan wanted something more ambitious. A record that could actually convey sounds and images, not just symbols. He assembled a small team, including his colleagues, Frank Drake, Anne Druyan, Timothy Ferris, John Lomberg, and Linda Salzman Sagan, to create the content. They had less than 6 months to complete the project before Voyager's launch. The record contains 116 images, encoded in analog form using the same basic technology as a vinyl record. The images are stored as audio signals that can be converted back into pictures using the instructions provided on the record's cover. The images show scenes from Earth, pictures of people from different cultures and ethnicities, wearing different clothing, engaged in different activities. A woman nursing a baby, children playing, people eating, a family portrait, pictures of animals, an elephant, a dolphin, a snake, an eagle, insects, fish, landscapes, mountains, deserts, oceans, forests, rivers, a sunset, human structures, the Great Wall of China, the Taj Mahal, a house, a bridge, a city skyline at night. Scientific diagrams showing human anatomy, DNA structure, cell division, the structure of atoms, mathematical and physical concepts, the spectrum of light, the definition of basic units. Pictures showing Earth from space, the solar system, and diagrams explaining Earth's location in the galaxy. The selection of images was carefully considered. The team wanted to show the diversity of life on Earth, while avoiding images that might be too culture-specific or that might convey the wrong message. For example, they avoided images of war or violence. They wanted to present humanity and Earth in a positive light, showing cooperation, curiosity, and the beauty of our planet. The record also contains greetings in 55 languages, from ancient Sumerian to modern Mandarin. Each greeting is just a few seconds long, spoken by native speakers. Some are formal, greetings from the inhabitants of this world. Others are more casual, hello from the children of planet Earth. Some are poetic, peace and happiness to all. The greetings represent the linguistic diversity of humanity, showing that we speak many different languages but share a common desire to communicate and connect. In addition to the spoken greetings, there's a greeting from then United Nations Secretary-General Kurt Waldheim, recorded in English. And there's a greeting from then President Jimmy Carter, also in English, that reads, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time, so we may live into yours." It's a message that acknowledges both humanity's achievements and our fragility. We are attempting to survive our time. We don't know if we will succeed, but we hope that if someone finds this record in the distant future, they will know that we tried, that we cared, that we wanted to reach out across the cosmos. The record contains sounds from nature. Wind blowing through trees, rain falling, thunder rumbling, waves crashing on a beach, a volcanic eruption, animal calls, the song of a humpback whale, birds chirping, dogs barking, frogs croaking, crickets chirping, human sounds, footsteps, laughter, a baby crying, a heartbeat, the sound of a kiss. These are sounds that define our world, the acoustic environment of Earth. Some would be familiar to any intelligent species with hearing. The sound of water, the sound of wind. These are universal phenomena that would exist on any planet with an atmosphere. Others are unique to Earth. The call of a whale, the laughter of a human child. The record contains 90 minutes of music from around the world. Bach's Brandenburg Concerto No. 2. Beethoven's Fifth Symphony. Mozart's Magic Flute. Stravinsky's Rite of Spring. Classical Western music, representing centuries of European musical tradition. But the team didn't limit themselves to Western classical music. They included music from many cultures. A Pygmy girl's initiation song from Zaire. A Navajo night chant. Japanese shakuhachi flute music. Indian raga. Chinese kin music. Peruvian panpipes. Georgian folk songs. A Senegalese percussion piece. Mexican mariachi music. And they included some modern Western popular music. Chuck Berry's Johnny B. Good, a rock and roll song from the 1950s. Louis Armstrong playing Melancholy Blues. Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a blues song from the 1920s. The selection of music was one of the most challenging aspects of the project. How do you choose 90 minutes of music to represent all of human musical achievement? What do you include, and what do you leave out? The team tried to balance Western and non-Western music, ancient and modern, instrumental and vocal. They tried to show the diversity and complexity of human music making. But they also knew that no selection could be truly comprehensive. Any choice would leave out far more than it included. In the end, they chose music that they felt represented important aspects of human culture and that they hoped would be interesting or beautiful to any listeners, human or alien. The record is designed to last for billions of years. Gold doesn't corrode in the vacuum of space. There's no oxygen to oxidize it, no water to dissolve it, no bacteria to break it down. The grooves in the disc, which encode the images and sounds, will remain intact essentially forever unless the disc is physically damaged. The aluminum cover protects it from most minor impacts with dust grains or small particles. If a larger object hits the spacecraft hard enough to damage the record, it would likely damage or destroy the entire spacecraft anyway. So the record's survival is tied to Voyager's survival. In 1 million years, assuming Voyager hasn't been destroyed by a collision or torn apart by tidal forces near some massive object, the golden record will still be there. Its information still readable by anyone with the technology to decode it. Of course, decoding it requires understanding how analog records work. The record includes instructions engraved on the aluminum cover. There's a diagram showing how to extract the audio signal from the grooves. There's an indication of the playback speed, defined in terms of the transition frequency of hydrogen atoms, a fundamental physical constant that any technological civilization would know. There's a diagram showing how to decode the images from the audio signal, including the scanline format and the duration of each image. There's even a diagram showing how to construct a stylus to play the record. But these instructions assume a certain level of technological sophistication. The aliens who find Voyager would need to understand concepts like electromagnetic radiation, atomic structure, and information encoding. They would need technology capable of detecting and analyzing the spacecraft, extracting the record, and building a playback device. That's a tall order for an alien civilization that might have evolved along completely different technological pathways. They might use different physics, different mathematics, different approaches to information storage and retrieval. They might not even have a sense of hearing. If they're a species that communicates by bioluminescence or telepathy or some other means we can't imagine, the sounds on the record might be meaningless to them. But the record wasn't really designed with practical communication in mind. Carl Sagan and his team knew the chances of Voyager ever being found by an alien civilization are vanishingly small. The spacecraft is tiny, traveling through an almost infinitely vast space. The probability that it will pass close enough to an inhabited planet for anyone to detect it is essentially zero. Even if there are millions of intelligent civilizations in the galaxy, they're spread across billions of cubic light-years of space. Voyager is a needle in a cosmic haystack, so large that the analogy barely makes sense. The record was designed as a statement, a gesture of hope and curiosity. A way of saying, we were here, we existed, we made this and sent it out into the universe because we wanted to reach out, to communicate, to connect with something beyond ourselves. It's a message to the future, to civilizations billions of years from now, when our sun has become a red giant and Earth has been destroyed. In that far future, long after humanity is gone, Voyager and its golden record might be the only remaining evidence that we ever existed. A lonely ambassador drifting through the dark, carrying the sounds and images of a world that no longer exists. Carl Sagan described the golden record as a message in a bottle cast into the cosmic ocean. Most messages in bottles are never found. They drift for years, decades, centuries, gradually deteriorating until they sink or wash up on some remote shore, their contents lost. But a few are found. Someone walking on a beach picks up the bottle, reads the message inside, and for a moment, there's a connection across time and space between the person who wrote the message and the person who found it. The golden record is humanity's message in a bottle. We don't know if anyone will ever find it. We don't even know if anyone else is out there to find it. But we sent it anyway, because the act of sending it matters. It says something about who we are or who we want to be. A species that looks up at the stars and wonders. A species that builds machines to explore the cosmos. A species that creates music and art and science and wants to share those creations with whoever might be listening. In 1 million years, the golden record will still be carrying that message, still traveling through the darkness, still waiting for someone to find it and hear the sounds of Earth. 1 million years is a timescale that's almost impossible for the human mind to grasp. Human civilization, in the sense of permanent settlements and agriculture, has existed for maybe 10,000 to 12,000 years. Recorded history goes back about 5,000 years. The entire span of human existence as a species, Homo sapiens, is roughly 300,000 years. 1 million years is more than 3 times longer than our species has existed. To put this in perspective, 1 million years ago, our ancestors were not yet modern humans. They were Homo erectus, walking upright, but with brains significantly smaller than ours. They used simple stone tools, controlled fire, but had no language as we understand it, no art, no agriculture, no cities, no writing. The entire arc of human development, from those primitive tool users to modern civilization, from the first crude hand axes to spacecraft and computers and the internet, all of that happened in less than 1 million years. Everything that makes us human, everything we've built and discovered and created, is contained within a time span shorter than the journey Voyager will complete. Now, imagine that same span of time extending forward from today. 1 million years into the future is as far ahead of us as we are ahead of Homo erectus. The changes will be at least as profound. In 1 million years, evolution will have had enough time to create new species from existing populations. If humans still exist, they will almost certainly have evolved into something different, something we might not recognize as human. Our bodies might have adapted to different environments, different gravity, different atmospheres. Our brains might have grown larger or smaller or restructured entirely. We might have split into multiple species, each adapted to different niches, like Darwin's finches on different islands. Or we might have taken evolution into our own hands, genetically engineering ourselves into forms optimized for space travel, for longevity, for intelligence. Or we might have transcended biology entirely, uploading our consciousness into machines or merging with artificial intelligence in ways we can't currently imagine. The boundary between biological and artificial might have dissolved completely. What we call human might be something unrecognizable to us, a hybrid of organic and synthetic, of evolved and designed. Or we might be gone entirely, extinct, our species having run its course like 99% of all species that have ever existed on Earth. Climate change, nuclear war, asteroid impact, pandemic, artificial intelligence gone wrong, any number of catastrophes could end us. Or we might simply fade away, our birth rates declining, our civilizations collapsing, until the last human dies alone somewhere, and the species that dominated Earth for a brief moment fades into evolutionary history. Empires rise and fall on timescales of centuries. The Roman Empire lasted about 500 years in the West, longer in the East. The British Empire peaked and declined in roughly 300 years. Every great civilization we know of has eventually collapsed, transformed, or been absorbed into something else. Civilizations last, at most, a few thousand years before transforming into something else. Ancient Egypt lasted about 3,000 years, but the Egypt of the Old Kingdom was profoundly different from the Egypt of the Ptolemaic period. The language changed, the religion changed, the political structure changed, the technology changed. By the end, ancient Egyptians could no longer read the hieroglyphs their ancestors had carved thousands of years earlier. Languages change so much over 1,000 years that they become mutually unintelligible. English, 1,000 years ago, Old English, is barely recognizable to modern English speakers. If you could somehow speak to someone from the year 1026, you wouldn't understand each other. Their English would sound like a foreign language to you, and yours would sound equally foreign to them. Go back 10,000 years, and whatever languages people spoke have left no trace. We don't know what they sounded like, how they were structured, what they could express. They're gone, vanished completely, along with the cultures that spoke them. Now, multiply that by 100. 1 million years from now, whatever languages exist, if language still exists in any form, will have nothing in common with the languages we speak today. Not a single word, not a single grammatical structure, not a single sound. It will all be completely different, evolved beyond recognition. The cultures, the beliefs, the knowledge we have now will all be forgotten, transformed, or replaced. Our religions, our philosophies, our scientific theories, our art and literature and music, all of it will be ancient history, if it's remembered at all. Future civilizations might study us the way we study ancient Sumerians or Neanderthals, piecing together fragments of our existence from archaeological remains, trying to understand what we believed and how we lived. or we might be completely forgotten. Our cities crumbled to dust, our digital records long since decayed, our very existence unknown to whoever comes after. And yet Voyager will still be out there, carrying its golden record with sounds and images from a world and a time that no longer exists, traveling through the darkness in a journey that has no destination and no end. There's something profoundly beautiful and profoundly sad about Voyager's journey. Beautiful because it represents the best of what humanity can do. The curiosity to explore, the ingenuity to build machines that can survive the harshness of space, the hope that somewhere, somehow, we might not be alone in the universe. Voyager is a testament to the human drive to reach beyond ourselves, to push the boundaries of what's possible, to leave a mark on the cosmos. Think about what it took to build Voyager. Thousands of people working together over many years. Engineers designing systems that had to work perfectly for decades, with no possibility of repair. Scientists choosing instruments that would still be relevant years after launch. Programmers writing code that would run on computers less powerful than a modern calculator. Technicians assembling components with incredible precision. All of this happening during a time when space exploration was still relatively new, when we were still learning how to build spacecraft that could survive the journey to the outer planets. The Voyager project required coordination across multiple NASA centers. The Jet Propulsion Laboratory in Pasadena, California, managed the overall mission. Engineers at various NASA facilities designed and built different subsystems. Universities contributed scientific instruments. Private contractors manufactured specialized components. Everyone had to work together, sharing information, solving problems collaboratively, meeting strict deadlines. The spacecraft had to be designed for reliability above all else. There would be no second chances, no opportunity to fix anything that broke. Every system had to work the first time and keep working for years. Engineers built in redundancy wherever possible. Critical systems had backups that could take over if the primary system failed. The computers could switch between different modes of operation if one mode encountered problems. The instruments could be shut down and restarted remotely if they malfunctioned. But even with all this redundancy, the spacecraft still had to be fundamentally sound. The materials had to withstand extreme temperature swings, from the intense heat near the sun during launch to the frigid cold of the outer solar system. The electronics had to survive radiation from Jupiter's magnetosphere, doses strong enough to kill a human in minutes. The mechanical systems had to operate smoothly after years of dormancy in the vacuum of space. Testing was exhaustive. Every component was tested individually, then tested again as part of a larger system, then tested again as part of the complete spacecraft. Engineers simulated the conditions Voyager would encounter, exposing prototypes to extreme temperatures, vacuum, radiation, vibration. They ran computer simulations of the trajectory, calculating every gravitational influence, every course correction, every moment when an instrument would need to be activated or shut down. The Voyager project cost about $865 million in 1977 dollars. That's roughly $4 billion in today's money. A massive investment, but consider what we got for it. 2 spacecraft that revolutionized our understanding of the outer solar system. Images and data that changed textbooks and inspired generations of scientists. Discoveries that fundamentally altered how we think about planetary science, about the possibility of life beyond Earth, about the diversity of worlds in our cosmic neighborhood. And now, 48 years after launch, one of those spacecraft is still functioning, still sending back data from beyond the edge of the solar system. No one expected Voyager to last this long. The engineers designed for a 5-year mission, maybe 10 years if everything went perfectly. They built in margins of safety, of course, but they couldn't have predicted that Voyager would still be operating nearly half a century later. The fact that it is speaks to the quality of the engineering and the dedication of the mission team. Every year, as the power from the RTG decreases, the team makes difficult decisions about which instruments to shut down. They've turned off the cameras because there's nothing to photograph in interstellar space. They've shut down heaters to conserve energy, accepting that some components will get colder than originally designed. They've turned off instruments that have completed their scientific mission. One by one, Voyager's systems are being put to sleep, carefully managed to extract every last bit of useful data before the power finally runs out. But a few instruments are still running. The cosmic ray detector, measuring high-energy particles from outside the solar system. The magnetometer, studying the weak magnetic field of the interstellar medium. The plasma wave instrument, detecting the subtle vibrations in the charged particles around the spacecraft. The low-energy charged particle detector, measuring the transition from solar particles to interstellar particles. These instruments are still gathering data that no other spacecraft has ever collected. As long as the power holds out, Voyager will continue its mission of exploration, sending back information about a region of space we've never studied before. But it's also sad, because Voyager's journey is ultimately a journey into oblivion. The spacecraft will almost certainly never be found. It will never complete its mission of communicating with another intelligent civilization. It will just drift, silently, through the vast empty spaces between stars for millions or billions of years, until perhaps it falls into a star or is torn apart by tidal forces near a black hole, or simply disintegrates slowly over eons from impacts and radiation. Think about the loneliness of that journey. Voyager is traveling away from the only home it has ever known, away from the beings that built it, into a darkness so complete that it's almost incomprehensible. Right now, Voyager is farther from any human being than any object in history. The astronauts who traveled to the Moon were about 239,000 miles, or about 384,000 kilometers, from Earth. That's close enough that they could see Earth as a disk, could communicate with mission control in real time with only a 1-second delay. Voyager is about 15 billion miles, or about 24 billion kilometers, from Earth. That's 62,000 times farther than the Moon. From Voyager's perspective, if it could have a perspective, Earth is invisible. The Sun is just another star, brighter than most, but not special. Everything Voyager has ever known, everyone who ever built it, or worked on it, or cared about its mission, is contained in a tiny point of light that's indistinguishable from all the other stars in the sky. And every second, Voyager moves farther away. Every day, it travels about 900,000 miles, or about 1.5 million kilometers. Every year, about 326 million miles, or about 525 million kilometers. The distance grows and grows, and there's no way to stop it, no way to bring Voyager back. It's gone forever. In a few more decades, it will go silent, its power finally exhausted. The last transmission from Voyager will be received at one of the Deep Space Network stations, the giant radio dishes that have been listening to Voyager's faint signal for decades. The signal will fade out, growing weaker and weaker until finally it's lost in the noise. And then there will be silence. No more data, no more transmissions, no more communication. Voyager will continue its journey, but we won't know where it is anymore. We won't know if it's still intact, if it's been hit by something, if it's passed close to any interesting objects. It will be beyond our reach, beyond our knowledge. All we'll have are the calculations, the trajectory predictions based on the last known position and velocity. And even those will become uncertain over time, the small errors accumulating until we've lost track entirely. But maybe that's okay. Maybe the value of Voyager isn't in where it's going or what it might achieve. Maybe the value is in the act of sending it. In the fact that we built it and launched it and sent it out into the universe, knowing full well that we would never see it again, never know its ultimate fate, never receive any benefit from it beyond the data it sent back in its first few decades. We did it anyway, because we wanted to reach out, because we wanted to explore, because we wanted to say to the universe, we are here, we exist, and we wonder what else is out there. That impulse, that desire to explore and discover, is one of the defining characteristics of our species. We've always been explorers. Our ancestors left Africa tens of thousands of years ago and spread across the globe, crossing oceans and mountains, settling in environments from Arctic tundra to tropical rainforests. They didn't have maps or compasses or GPS. They just walked, following rivers and coastlines, always moving, always wondering what was over the next hill or beyond the next horizon. The first humans to cross the Bering Land Bridge into the Americas walked into a completely unknown continent. They had no idea what lay ahead, how far the land extended, what dangers or opportunities awaited them. But they kept walking, generation after generation, spreading south through North America, Central America, South America, all the way to Tierra del Fuego at the southern tip of the continent. A journey of thousands of miles, undertaken on foot, over thousands of years, by people who would never see the destination, but who kept moving anyway. The Polynesians, who settled the Pacific Islands, embarked on some of the most audacious voyages in human history. They sailed across thousands of miles of open ocean in small canoes, navigating by the stars, the waves, the flight patterns of birds. They left from islands like Tahiti or Samoa and sailed into the vastness of the Pacific, not knowing if they would find land or drift until they died of thirst. Many expeditions failed. Many canoes were lost, their crews vanished into the ocean, their fates unknown. But some succeeded, finding tiny islands scattered across the Pacific, establishing new settlements, and then setting out again to find the next island. This is how humanity settled every habitable place on Earth. Through exploration, through risk-taking, through a willingness to venture into the unknown, even when success was far from guaranteed. Some of them died in the attempt. Many of them failed to find what they were looking for. But they kept going, driven by curiosity and the hope that there was something better, something new, something worth discovering. That same impulse drove the European age of exploration in the 15th and 16th centuries. Ships setting sail across uncharted oceans, not knowing if they would find land or fall off the edge of the world. Christopher Columbus sailed west into the Atlantic in 1492 with 3 small ships and a crew of about 90 men. He thought he was sailing to Asia. He had no idea that 2 vast continents lay between Europe and Asia, blocking the route he thought he was taking. If the Americas hadn't been there, his ships would have run out of food and water long before reaching Asia, and everyone aboard would have perished. He was lucky, in a sense, though his arrival in the Americas would prove catastrophic for the people already living there. Ferdinand Magellan's expedition to circumnavigate the globe set sail in 1519 with 5 ships and about 270 men. Only one ship returned, 3 years later, with just 18 survivors. Magellan himself was killed in the Philippines. Most of his crew died from starvation, disease, shipwreck, or violence. The voyage proved that the Earth was round and much larger than previously thought, but the cost was enormous. Yet, despite these losses, the voyages continued. Many ships were lost. Many sailors perished from scurvy, drowning, piracy, disease. But they kept sailing, and eventually they mapped the entire globe, connecting continents that had been isolated for tens of thousands of years. That same impulse drove the space race in the 20th century. The decision to go to the moon, not because it was easy, but because it was hard. President John F. Kennedy's speech at Rice University in 1962 captured this perfectly. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. The willingness to risk lives and spend vast resources to achieve something that had never been done before. The Apollo program cost about $25 billion in 1973 dollars, over $150 billion in today's money. It required the work of over 400,000 people at NASA, universities, and private contractors. 3 astronauts died in the Apollo. 1 fire during a launch pad test in 1967. Others risked their lives flying to the moon, trusting technology that was brand new and largely untested. Apollo 13 nearly ended in disaster when an oxygen tank exploded, forcing the crew to abort the moon landing and loop around the moon to get back to Earth. They survived only through ingenuity, quick thinking, and a spacecraft that held together under conditions it was never designed for. But we kept going, and in July 1969, Neil Armstrong and Buzz Aldrin walked on the moon while Michael Collins orbited above. It was one of humanity's greatest achievements, a moment when we proved we could leave our planet and set foot on another world. And that same impulse drives Voyager's journey. We sent it out into the cosmos, not because we expected it to return valuable resources or establish colonies or make contact with aliens. We sent it because we wanted to see what was out there. Because we wanted to know. Because the universe is vast and mysterious and beautiful, and we are a curious species. Voyager is the physical manifestation of that curiosity. A machine we built to go places we cannot go, to see things we cannot see, to answer questions we've been asking since we first looked up at the stars and wondered. It's part of a long tradition of exploration that stretches back to our earliest ancestors who first walked out of Africa and continues forward into an unknowable future. Let me put this in perspective one more time. Voyager 1 launched on September 5, 1977. It's now been traveling for over 48 years as of 2026. In that time, it has covered about 15 billion miles, or about 24 billion kilometers. That sounds like an enormous distance, and it is. But 1 million years from now, Voyager will have traveled about 333 trillion miles, or about 536 trillion kilometers. That's roughly 22,000 times farther than it's traveled so far. If we scaled down Voyager's current distance from the Sun to the size of a single step, about 3 feet or about 1 meter, then the distance it will travel in 1 million years would be about 14 miles, or roughly 22 kilometers. A journey that started with a single step will, in 1 million years, have covered the distance of a marathon many times over. And yet, in the context of the galaxy, Voyager will have barely moved. The Milky Way is about 100,000 light-years across. Voyager will have traveled 56,000 light-years, which sounds like more than halfway across the galaxy. But remember, Voyager isn't moving across the diameter of the galaxy. It's moving through a small region of one spiral arm. The stars around it will have shifted positions. The Sun will have moved along its orbit, but the overall structure of the galaxy will be essentially unchanged. From a galactic perspective, Voyager's journey is a tiny, insignificant movement, a mote of dust-shifting positions slightly in a vast cosmic structure. And yet, from a human perspective, it's the farthest we've ever sent anything, the longest journey we've ever begun, a mission that will outlast our civilization and possibly our species. There's one more thing worth considering. Voyager 1 is not alone. Its twin, Voyager 2, launched 16 days before Voyager 1, but followed a different trajectory. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune before heading out into interstellar space in a different direction. In 1 million years, Voyager 2 will be in a completely different part of the galaxy, tens of light-years away from Voyager 1. The two spacecraft, built together, launched together, will have diverged completely, each on its own solitary journey. They will never meet again. They will never even be close again. They are, in a very real sense, siblings who have gone their separate ways, never to reunite. In addition to the two Voyagers, there are other human-made objects heading out of the solar system. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also traveling through interstellar space, though they stopped transmitting decades ago. New Horizons. The spacecraft that flew by Pluto is also on a trajectory that will eventually take it out of the solar system, though it's moving slower than the Voyagers and won't reach interstellar space for many more years. All of these spacecraft are heading in different directions, spreading out across the galaxy like seeds scattered by the wind. In 1 million years, they will be scattered across a region, hundreds of light-years across, each traveling alone through the darkness, each carrying some remnant of humanity's early ventures into space. They are our first, and so far only, interstellar emissaries. They represent the first time in Earth's history that something from our planet has left the solar system and entered the larger cosmos. Before Voyager, everything humans had ever made, every object, every structure, every machine, stayed within the sun's gravitational influence. Now, we have sent pieces of ourselves beyond that boundary, into a realm we may never reach ourselves. So where will Voyager 1 be in 1 million years? It will be roughly 56,000 light-years from where the Sun is at that time. It will be traveling through the Milky Way's Orion Arm, or perhaps at the edge of it, moving through regions of space populated by stars we don't even know about yet. It will be cold, dark, and silent, its power long exhausted, its systems long dead, it will have passed by countless stars, though none close enough to significantly alter its path or pose any danger. It will have traveled through gas clouds, dust lanes, and empty voids, each region leaving no mark on its journey. It will still be carrying the golden record, humanity's message to the cosmos, intact and readable, waiting for someone who will almost certainly never come. And it will still be moving, still traveling at about 10.5 miles per second, or about 17 kilometers per second, still following the trajectory set when it left Saturn's gravity well more than 1 million years earlier. Voyager's journey is, in many ways, a metaphor for humanity itself. We are small, fragile, temporary beings living on a small, fragile, temporary world. We exist for a brief moment in cosmic time, and then we're gone, replaced by whatever comes next. But while we're here, we reach out. We explore. We build. We send our creations out into the universe, even knowing they will almost certainly never return, never be found, never achieve their purpose. We do it because we can, because we're curious, because somewhere deep in our nature, there's a drive to leave a mark, to say we were here, to touch the stars, even if only symbolically. Voyager 1 is that mark. It's a small, silent machine, carrying the hopes and dreams of a species that wanted to reach beyond itself. In 1 million years, when Voyager is drifting through regions of space unimaginably far from its origin, the humans who built it will be long gone. The Earth they knew might not exist anymore. The civilization that created it will have transformed or vanished. But Voyager will still be there, still traveling, still carrying its message. And in that persistence, in that lonely journey through the darkness, there's something profound, a reminder that even though we are small and temporary, we can create things that endure. We can reach farther than ourselves. We can touch eternity, if only for a moment. Voyager 1, humanity's farthest traveler, will spend the next 1 million years proving that we were here, that we looked up at the stars and wondered, and that we had the courage to send a piece of ourselves out into the unknown. Thank you for following this journey with me across space and time. The next 1 million years of Voyager's voyage will unfold in silence and darkness, with no one watching and no one knowing. But tonight, for this brief moment, we've traced its path, imagined its future, and honored the incredible achievement it represents. Keep looking up. The universe is vast and strange and beautiful. And somewhere out there, traveling through the darkness, a small machine we built carries a piece of us toward the stars.